Let's go through the process of finding a p-value using StatKey and then how we can simulate that process without StatKey. In this example, we're looking at a hypothesis test for a mean, and because we see that it is for a mean, which we can tell by the fact that we are given a sample statistic that's called x bar, and that our hypotheses are in terms of mu, these two things together tell us that we have a t-distribution. And the fact that we have n equals 25 here tells us that our t-distribution has n minus 1, or 24 degrees of freedom. So from our hypotheses, we can also tell that we want a right tail test, which we see from the alternative hypothesis, the fact that it has a greater than. We want the right tail of a t-distribution with 24 degrees of freedom. And our test statistic tells us where that tail should start. We don't go through the computations in this example because we really want to get quickly to the point, but we can see in these computations that we would first calculate a standard error and then use that standard error in the denominator of our test statistic formula to get a t-statistic, and that here at the end we have our actual t-statistic that we're going to use in order to find the p-value. So we want a t-distribution 24 degrees of freedom with a right tail starting at 1.863. Let's first go do that in StatKey. Coming to StatKey, I would go to Theoretical Distributions T. So coming here, it's going to prompt me for degrees of freedom, at which point I enter 24. And I know I want a right tail, and I want that right tail to start at 1.863. So I go ahead and overwrite the boundary value with 1.863. I get a p-value of 0.037. from StatKey. Now, the estimate that I'm going to get without software is not going to be quite this precise, but I'll be able to see that it's close enough to this value that I would still get the same conclusion, which is really the most important part. Sometimes we don't know exactly what the p-value is, but we can narrow it down enough that we can still write a reasonable conclusion. To do this process without software, we need to refer to our right tail p-values graphs and first select the correct graph. We decided that we had 24 degrees of freedom in a t-distribution, so I'm going to choose the t-distribution with 20 to 29 degrees of freedom. Now I also found that my t-statistic was 1.863, which is pretty close to 2, but not quite there. I would definitely mark that to the right of this 5% line, since that 5% line looks like it's closer to 1 3/4 or 1 2/3, which would be a little bit smaller than this 1.863. So here I'm going to mark t equals 1.863, and I'm going to fill in a line going up from here and shade that right tail. From this graph, I can see that we are to the right of the 5% line, so I can tell that my p-value is less than 5%. I can see that we were to the left of the 2.5% line, so our p-value should be more than 2.5%. So I'm going to come up with a number that's between these, and really any number that's between these two bounds is reasonable. I'm going to just say that that p-value is 0.04, thinking that it's a little bit closer to the 5% than to the 2.5%. If we came up with an estimate of 0.03, that would also be fine. We just really want to get it in between the bounds that are known. So since I've marked up this graph for question number 1, I'm going to go ahead and label it number 1, and now I'll go back and put my answer in the blank. My estimate of the p-value is 0.04. I can see that the StatKey value is a bit more accurate. From StatKey we got 0.037 and our estimate is 0.04, so that they're not exactly the same, but they would both give us statistical significance at the 0.05 level. They would both fail to reject at the 0.01 level, right? So they're still within the same range of different commonly used statistical significance levels. Now let's look at a couple more examples just to make sure that we know what to do when we have a proportion and we know what to do when we have a left tail or a two-tail test. So on this next one we can see that our sample statistic is a proportion. It's a p-hat, and that our hypotheses are written in terms of p. Both of those are clues that we're talking about a test of one proportion. And when we're doing a proportion, we would not use a t-distribution, we would use a normal distribution. We don't calculate degrees of freedom for a normal distribution. That only comes into the t-distribution. So I'm not going to take this 10 and do n minus 1 and use that for anything at all. There's only one standard normal distribution that we use for all of our inference. Looking at our hypotheses, we can also see that we have in our alternative hypothesis that p is not equal to 0.75, which tells us that we have a two-tail test this time. We also can see the computations that went into the z statistic. We call it z now because it's a normal distribution. First calculating that standard error, and again then using that standard error in the denominator of our z statistic calculation, so that what we end up with here at the very end is our z statistic. I am now going to go to the normal distribution in my graph chart. I can see different t distributions with different degrees of freedom. Once the degrees of freedom get to 30 or higher on a t distribution, for p-values we go ahead and use the normal distribution. Just because we're not getting a very precise p-value anyway, it doesn't really make sense to need a different graph for each of these ones that are all pretty close together. So we'll go straight to the t with 30 degrees of freedom or more, or a normal distribution. In this case we're choosing it because it's a normal distribution. And I'm going to mark my z statistic here on the number line just a little bit to the right of 1. That was 1.096, I believe. Let's make sure. Yep, 1.096. So that's really close to 1.1, which is about 1 1/10. So we really want it pretty close to that 1 there. And then I'm going to fill in my line going up and shade the tail. We can, of course, see that this is a fairly large tail at this point, and in fact, we are greater than that 10%, right? Because our shaded area started a little bit to the left of that line. So we're looking at more than 10% for this p-value, but it's even more than that because remember we're doing a two-tail test. So really our shaded region has got a symmetric part over on this side that we can also shade in, and in fact we must also shade that in to demonstrate that we know that we're using both tails. So our actual p-value estimate has got to be a little more than 20%, a little bit greater than 0.20. Maybe let's go ahead and just say 0.22 or 0.25, right? go ahead and say 0.22, even though it's probably a little bit bigger than that. This p-value is big enough that we can tell that we would fail to reject under any reasonable significance level, and that we would say we don't have any statistically significant evidence that the alternative hypothesis is true. So our estimate is 0.022, and again, it's not about getting the most accurate possible estimate, although it is nice to try to get it a little bit more accurate than necessary. It's really about getting a good enough estimate of the p-value. Sorry, I put an extra 0 in there. It's really about getting a good enough estimate of the p-value that you can write an accurate conclusion. So let's look at one more example. And again, we have a mean, which we can see from the fact that we're given a sample statistic x bar and that our hypotheses are in terms of a mean mu. So because this is a mean, we would use a t-distribution, and our degrees of freedom, from the fact that n equals 400, we want then 399, which is n minus 1 degrees of freedom. In this case, we can see that our alternative hypothesis has a less than, which tells us that we have a left tail test. So let's go ahead and take our t-statistic of negative 3.509 to the appropriate graph and find a p-value. Looking at our options, we're going to again select the t with 30 plus degrees of freedom or normal, but this time we're selecting it not because we want a normal distribution, because our degrees of freedom are so high. As soon as our degrees of freedom get above 30, we go ahead and use the one that's equivalent to normal, at least for purposes of finding a p-value. This is just because our p-value estimates aren't very accurate anyway. So on here I'm going to estimate 3.509, which is really close to 3.5. So let's label that with a T. Oops, sorry about that. Because I didn't have it right in front of me, I forgot it's actually negative 3.509. So t equals negative 3.509 over here on the left. My left tail then is going to be this part I can hardly even shade. I try to go over it with another color anyway to make it stand out because I want to always have some sort of region to shade. At this point I really have to look at the markings on the right tail to try to figure out what my p-value estimate is for the left tail. So I'm going to put a mark here at 3.5 just for my own purposes and see that it is past the mark for 0.5%, and that means that this symmetric tail over here is also less than 0.5%. So this is less than 0.5%, which means that it's overall less than 0.005. So I want to come up with an estimate of that p-value that is less than 0.005. It looks like it's substantially less, so I'm going to go all the way down to 0.001 as my rough estimate of the p-value. So my rough estimate of the p-value for this left tail test is 0.001. We can see it's a very small p-value, and we would reject the null hypothesis for pretty much any significance level that we're given, or we would say that we have very strong or overwhelming evidence for the alternative hypothesis.